Now, in this lecture, we will study briefly about the Z bus or the bus impedance matrix. In our next lecture, we will derive an algorithm to find the bus impedance matrix for a given network, because we can directly find the bus impedance matrix by inverting the admittance matrix, but usually the values given are complex in quantity, so the calculation becomes cumbersome. So we try to find an algorithm such that the calculations become easy, but there is a catch into it. The number of calculations increase in that algorithm. So we will study that algorithm in the next lecture. Now we will study briefly about what is Z bus and what are its properties. As I already told that Z bus is nothing but the inverse of Y bus, and we have already seen how to determine the bus admittance matrix. So if I invert this matrix, then I will get the Z bus. Now we also know that if the elements present in the network are linear and bilateral, then the Y bus will be symmetric. So if any tap changing transformers or off-nodal tap changing transformers are not present in the network, then this matrix will be symmetric. Now there is a property that if a matrix A is symmetric, then its inverse is also symmetric. So this implies that the bus impedance matrix, the G bus, will also be symmetric. Now how to derive this? For a symmetric matrix, we know that A transpose is equal to A. Okay. Now the I matrix, the unity matrix, is also a symmetric matrix. Now A inverse into A transpose is equal to I. Now if I take this whole transpose, A inverse into A transpose and their transpose will give me this equation. Now taking this transpose inside, what I will have? A transpose transpose and A inverse transpose, and as I already noted, this is just the unitary matrix. Now this is nothing but A into A inverse transpose is equal to I. Now from the matrix algebra, we know that for a given matrix A, its inverse is also unique. Okay, so if this is a given matrix A, then this matrix should be its inverse, so that I can get the unitary matrix. Okay, it implies A inverse transpose must be equal to A inverse, and now this implies that the A inverse matrix is also symmetric. So in this way, I have proved that if Y bus is symmetric, then Z bus is also symmetric. Now there is one more question usually asked, which is very simple. We already know that the bus admittance matrix, that is Y bus, is sparse in nature. What does it mean? That majority of the elements are 0 in the Y bus matrix. Now the question usually asked is about the sparsity of the G bus or the bus impedance matrix. Usually if Y bus is sparse, then G bus is not sparse, because the 0 elements in Y bus are usually non-zero in G bus. So then G bus is usually not sparse. Okay. Now in the next slide, we will try to see some of the properties of Y bus and G bus. Now let us say that we are given a network in which these two equations are given. Although I can also write the third equation for the current I3, where I1 is nothing but Y11 into V1 plus Y12 V2 plus Y13 V3. Similarly, I2 is given by Y21 V1, Y22 V2 and Y23 V3. Now, from this equation, I can see that Y22 can be written as the ratio of I2 over V2 when V1 is equal to 0 and V3 is equal to 0. So let us say that the given network is such that this is bus number 1 and this is bus number 2 and this is the reactance between bus 1 and bus 2 and this is bus number 3 and this is the reference bus. Okay, and let us say currents are entering into the transmission system from these buses. This is I1, this is I2 and this is I3. Okay, the voltage here is V1, V2, V3. Now to find the Y22, what I need to do? I need to ground this V1. Similarly, I need to ground this V3. Okay. Now, from the given network or the given power system, I can see that I can redraw this power system like this. Let us say this is Y12, Y13, Y23. This is Y12, Y23, Y13. This is connected to ground and this is also connected to ground, or I can show that these two are connected to ground, and here the current entering is I2 and the voltage at this node is V2. Okay, now we can see easily that this can be neglected because it is already short circuited. Now I can clearly see that I2 over V2 is nothing but the parallel equivalent of these two elements, Y12 and Y13. Now these are admittances. Admittances add in parallel. So it is nothing but Y12 plus Y23. So you see that Y22 is nothing but the admittance which is directly connected to bus 2. The summation of all the admittances which are directly connected to the bus number 2, which we have already seen in our previous lectures also. Similarly, let us say I want to find another element Y12. y12 is nothing but the ratio of I1 over V2 when V1 is equal to 0 and V3 is equal to 0. Now I will have to redraw this network again. Here V1 is equal to 0, I have shorted it to ground. V3 is equal to 0, I have shorted it to ground. Okay, now I will redraw this given network. Now I have redrawn this network to find this ratio, which is I1 over V2 when V1 and V3 are equal to 0. Okay, now this element can be neglected because it is already shorted. Now I will redraw this here. I1 Y12 this is Y23. I2 V2. Now from this network I will try to calculate this ratio in the next slide. Now from the given network we can easily see that Y12 is nothing but the ratio of negative of current entering at node 1 and voltage at V2, which is nothing but the negative of this element. So Y12 is nothing but minus of Y12. It appears that I have gone too fast in determining Y12 by the ratio of I1 over V2 when V1 and V3 are 0. Let us see little bit in detail. In the lecture I have drawn a 3-bus system. Let us say this is bus 1, this is bus 2 and this is bus 3. I have also shown an admittance Y12, Y13, Y23. Current I1 is entering from node 1, current I3 is entering from node 2 and source current I2 is entering from node 2. Now these are the source current which are entering at the various buses or nodes. I also written an equation where it was shown that I1 is equal to Y11 V1 plus Y12 V2 plus Y13 V3. Now it is seen that Y12 can be written as ratio of I1 over V2 when V1 and V3 both are equal to 0. That is, this bus is shorted to ground and this bus is also shorted to ground or the reference bus. Okay, so if I do this, this network will transform into this given network Y12, and since both are grounded, so this admittance will be short circuited. And here is somewhere bus number 3, and these two are already grounded. Here a current I1 from source is entering at node 1, and here current I3 is entering at node 3, and here source current is I2. Now I have to find this ratio I1 over V2. There is a very subtle point in which we should know what is I1, I2 and I3. That is, whenever we write I is equal to YV, what does it mean? It means the source currents which are entering from a node to the transmission network. Okay, and this is the admittance matrix, and these are various bus voltages. Now, what do I want to say from this statement? That these currents are actually the currents which are entering the transmission network from the bus. Let us see what I want to say from this. Let us say this is bus 1 and it is having, let us say, various current sources I1, I2, so on, and the reactances of these current sources, let us say, are shown like this. Now let us say this bus is also having some load. And this bus is connected to the transmission network like this. Let us say now here is some transmission network with various buses. Okay, so here the current which will come into this current vector will be the only current which is entering this power system. Let us say it is I1 prime. So instead of this I1, what I will use I1 prime in the current vector in the equation given by I is equal to YV. So we should always note that these currents are the currents which are entering from the bus to the transmission network. Now we will see how we will use this concept in finding this ratio. Here V1 and V3 have been shorted out. So this whole current from the current source, let us say it is some current source, this whole current will be shorted to ground. Similarly, this whole current will be shorted to ground. So no current is being entered from this source and this source. Okay, so how to determine this ratio? What is I1 here? I1 will be actually the current entering here. Let us say I write it as I1 prime. Okay, so instead of writing I1 here, I will write I1 prime. Now what is it? Let us see how to find this. What I have done here a current source is attached on the bus 2, which is I2, and this current source is giving a current, let us say I2 prime. in this admittance, and here I have already shown I1 prime. Okay, and it is shorted. This current source is also shorted. Okay, this current is also shorted. Now this I2 is giving I2 prime in this admittance and I2 double prime in this admittance. Now from KCL I can see that I2 prime is equal to minus of I1 prime. Okay, so from this KVL, from this KVL loop, I can see that Y12 can be written as the ratio of I2 prime over V2, which is the voltage at this bus, V2. Okay, or I can see that Y12 can be written as minus of I1 prime over V2, or I can see that this ratio, which is equal to the admittance matrix element Y12, it can be written as minus of Y12 is equal to capital Y12 is equal to I1 prime over V2. So we see that Y12 can also be determined by shorting all other buses and putting a current source on, let us say, bus 2 and finding the ratio of I1 over V2, where I1 is the current which is entering into the transmission network from the bus 1. So now I hope that this point is clear, that how we are writing this Y12 as a ratio of a current and a voltage, and I hope that this point will also be clear that these currents are not actually the total source current. They might be different if there are some loads, local loads, which are available on the buses. So in that case, these currents are actually those currents which are entering from the bus to the transmission network. Now the remaining part of the lecture will continue. So in the matrix or the given admittance matrix, we have already seen in our previous lectures that the off diagonal elements are nothing but the negative of the elements which are connected between the given two nodes. So in this way, I can draw a equivalent passive network from the bus admittance matrix. Now in the next slide, we will see whether we can do similar calculations or similar network manipulation in the bus impedance matrix or not. Now for a given network, I can write using the Z matrix that V1 is nothing but Z11 I1 plus Z12 I2 plus Z13 I3, and V2 as Z12 or 21 I1 Z22 I2 plus Z23 I3. Similarly, I can also write V3. Now from this matrix, I can see that Z22 can be written as the ratio of V2 over I2 when I1 is equal to 0 and I3 is equal to 0. That is, if we are given a network like the previous network, this is bus 1, this is bus 2, and this is bus 3, and currents are entering to the transmission network. Let us say this is current I1 this is current I2 and this is current I3. This is voltage V1, this is voltage V2 and this is voltage V3. Now we had seen that for the admittance matrix we had to short the buses with the reference bus. However, to find the elements of the impedance matrix, instead of shorting the buses, we have to open the source currents, or we have to open these currents. So if I open this and open this, then we will be able to find Z22, which is nothing but Z22 will now be nothing but the ratio of V2 over I2, and since I have inactivated all the sources, then it is nothing but the impedance seen from the bus 2, or the Thevenin equivalent impedance at bus 2, or seen from bus 2. Okay, but you see that Z22 is not equal to the reciprocal of Y22, because Y22 was found by shorting the buses to the reference bus, but Z22 is being found by opening the current sources. So physically these cannot be equal. Okay, now one more thing. From the admittance matrix we could draw the equivalent passive network, but from the impedance matrix it is not possible to draw the equivalent passive network, because if I want to see that, I need to find, let us say, Z12. Z12 will be nothing but the ratio of V1 over I2 when I1 and I3 are 0. So this Z12 will try to give me the voltage at bus 1 when only the effect of source current at bus 2 is considered. So it is some kind of transfer impedance which tries to show the effect of the current, source current at a given bus, which will give a potential drop or potential at the other bus. Okay, so there is no physical way to show this Z12 as we could have easily shown in the admittance matrix. So you see that this is not physically realizable, or the network is not physically realizable just from the given values of the impedance matrix. So these are the major differences in the admittance matrix and the impedance matrix. Now in the next lecture what we will do, we will try to formulate an algorithm to find the impedance matrix for a given network. One method is just by inverting the admittance matrix, and the other method will be the algorithm which can be computerized to find the impedance matrix for any given network. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.